Our next topic is general circular motion. So we start like this. Suppose P moves in any manner, not necessarily with constant speed, around a circle with center O and radius B. Okay, so P is moving around this circle whose center is at O and whose radius is B. But the difference that this has with what we previously considered is that now the speed around the circle, the speed of P is not constant. The motion is not necessarily uniform circular motion. It is a circular motion, but it may be uniform, it may not be uniform. Now you can see in this diagram that we are having this line, which is our initial line, and this O is the pole. So that means we are going to use polar coordinates. Now because this distance is constant, it's a radius of the circle. So that is why in this case r is equal to b, which is constant. So the first time derivative and second time derivative of r are both equal to 0. Hence the velocity of p in polar coordinates is this. We have already discussed this before. R dot r hat plus r theta dot theta hat, where r hat is radially outward, from the pole it goes out, and theta hat is perpendicular to that. Because our r dot is 0, so this component is not there. This component is not there, we have only this component, which is this, r theta dot theta hat. But r is constantly b, that does not change, which is the radius. So that's why this is our velocity, b theta dot theta hat. Now this transverse velocity component b theta dot, which is the only one that we have here, the radial component is not there, is called the circumferential velocity of p. Okay, it's called that. However, the author also draws our attention to this, that this is not necessarily the speed of p, because although b is positive, but theta dot may be negative. For example, if theta is a decreasing function of time, then theta dot will be negative. And the author says that this will be important when we study rigid body motion, where a rigid body is rotating about a fixed axis. So when we see scalar angular velocity, we will see those things. And in such a motion, each particle of the rigid body is moving around a circle in a general manner, like this motion, so that the circles on which the particles are moving, they have their centers located on that axis of rotation. And the acceleration of p in polar coordinates is of course this, that more complicated formula that we have already derived in the previous video. R double dot minus r theta dot square times r hat plus r theta double dot plus 2r dot theta dot times theta hat. Because our r dot and r double dot are both 0, so this and this will vanish. And here we will just have minus r theta dot square times r hat. Because r is b, I have put b here. Similarly, this is not there, it's 0, and we have b theta double dot theta hat. And you can express this like this in terms of circumferential velocity that we saw just now, which is our b theta dot. If you multiply and divide by 1b, then you will have the square of b here in the numerator, so that way you are getting minus b square divided by b times r hat. And if you differentiate this, since b is constant, differentiate with respect to time of course, you are just going to differentiate this theta dot. So that's how you will get theta double dot. So this part is v dot. So that is your acceleration in general circular motion. Unlike velocity, which only has one component, acceleration is a linear combination of r hat and theta hat. And then we have example 2.7. The bob of a pendulum moves on a vertical circle of radius b. Obviously, when the bob swings like this, suspended on a string, the bob swings like this, it moves on a circle. So that circle is vertical, and say the radius of that circle is b. Now when the string makes an angle theta with the downward particle, the string originally, when there is no motion, it is itself vertical like this, right? But when it starts to swing, there is an angle. Say that angle is, when that angle is theta, that the string is making with the particle, then the circumferential velocity v of the bob is given by this formula. V squared equals 2gb cos theta, where b is our radius and where g is a positive constant. You already know what g is, okay? Acceleration due to Earth's gravity. Then we have to find the acceleration of the bob. When the angle is theta, that is also written, but we just have to find acceleration in general. So we are given that the square of the circumferential velocity equals 2gb cos theta. So what we now do, we differentiate this equation implicitly with respect to time. So the left hand side will be 2v times dv dt or v dot, and the right hand side will be minus 2gb, because cos theta, we have cos theta, so minus 2gb sin theta times d theta dt, that is theta dot. But you recall that the circumferential velocity v itself is b times theta dot. So you have v here. Then after cancelling 2v from both sides, you get v dot equal to minus g sin theta. So now we can write the acceleration of the bob, because we know both v square as well as v dot. V square is 2gb cos theta, and v dot right now we calculated minus g sin theta. So after cancelling b, you get this minus 2g cos theta r hat minus g sin theta theta hat. That's the acceleration of the bob when the angle that the string makes with the downward particle is theta. As theta changes, the acceleration also changes. The video ends here. Next week we are going to transition from single particle motion to rigid body motion.